the union of two disjoint countably infinite sets. Let's start with A is a countably infinite set, and B is a countably infinite set. And the two sets are disjoint, meaning their intersection is empty. Then A union B is countably infinite. Since A is countably infinite, we have a bijection from the set of positive integers to A. B is countably infinite, so there's a bijection from positive integers to B. We gave this second function a new name. We define H from positive integers to A union B and prove it's bijective. We don't know what the rules for F and G are, but we will reference those rules when we make the rule for H. While elements in a set are not technically in an order, informally let's think of f of 1 as the first element of A and f of 2 as the second element of A and so on. Similarly, let's visually write elements of B in order based on the function g. F of 3 might not be a number. 3 is a number, but f of 3 might be the third person on a bus. Likewise, g of 2 might be a person in hotel room 2. What do we want the rule for H to do? There are many ways to do it, but to make a predictable pattern, how about H of 1 equals f of 1, the first element of A, and H of 2 equals g of 1, H of 3 equals f of 2, H of 4 equals g of 2, and H of 5 equals f of 3, and H of 6 equals g of 3, and so on like this, alternating or zigzagging. If we do it this way, then H maps odd positive integers to elements of A, and H maps even positive integers to elements of B. If we are careful, each element of A union B appears as an output of H once and only once. The sequence 1, 1, 2, 2, 3, 3 has a piecewise formula. Focusing on the red values, when n is even, is easier first. We see that if n is even, then u sub n is found by dividing n by 2. The formula when n is odd is a little more work, but not much more. Of course, you can have 1/2 n plus 1/2 instead of n plus 1 over 2. Notice the points 1, 1, and 3, 2, and 5, 3, and so on form a line, and that line has slope 1/2 with y-intercept 1/2. So y equals 1/2 x plus 1/2 in algebra land becomes u sub n equals 1/2 n plus 1/2, but only for odd n. Let's recall what we wanted the rule for H to achieve. We haven't written a rule yet, but here's a table form of our wants. In table form, we want H of 1 equals f of 1, and H of 2 equals g of 1, and H of 3 equals f of 2, etc. So let's define H from the set of positive integers to A union B by the rule H of n is f of n plus 1 over 2 if n is odd, and H of n is g of n over 2 if n is even. Looking at the colors, how much of the u sub n formula did we borrow? Notice we specified a rule for H, even though we did not have specific explicit rules for f and g. We did, however, reference the rules of f and g as we made our rule for H. Having provided a domain, codomain, and rule for H, we now need to prove H is bijective. We start by proving H is surjective. We have f from positive integers to A and g, a function from the set of positive integers to be bijective. We defined H from the set of positive integers to A union B with a piecewise rule. Recall J from D to C is surjective if for all C in C there exists D in D such that J of D equals C. To prove H is surjective, we prove for all something in codomain, so let Y in A union B be arbitrary. We want to show there exists x in set of positive integers such that h of x equals y. From y in the union, y is in A or y is in B. We prove by cases. Suppose y is in A. What do we do with this information? We know f is surjective, and that translates to knowing a for all something in A is true. So we should use this for all something in A statement. Often we start with the for all something in set and then look for an element in that set. Here we started with an element in the set A, and we went looking for a way to combine y and A with something else, so it made sense to try to use for all something in A, which we know to be true. Since f is surjective, there exists c in positive integers such that f of c equals y. Let x equal 2c minus 1. We skip proving x is a positive integer. We also skip proving that x is odd. Summary, defining z equals c minus 1 leads to proving x is odd. And you get z by setting 2c minus 1 equal to 2z plus 1 and solving for z. So h of x equals f of x plus 1 over 2 using the first piece of rule for h. Substitute x with 2c minus 1, simplify negative 1 plus 1, cancel 2's, and a moment ago we said f of c equals y. So in this case, there exists an x in the set of positive integers such that h of x equals y. The only other possibility is y is in B. Since g is surjective, there exists a d in set of positive integers such that g of d equals y. Let x equal 2d. Note x is a positive integer. X is an integer since x is the product of integers. X is positive since both 2 and d are positive. Since d is a positive integer, d is an integer, so x is even. Use the other piece. H of x equals g of x over 2 equals g of 2d over 2 equals g of d equals y. In this case, we also have there exists a positive integer x such that h of x equals y. We defined an x in the set of positive integers such that h of x equals y in both cases. So h is surjective. Recall again, f and g are bijective, and the rule for h is here for reference. To prove h is injective, let p and q from domain be arbitrary. Suppose the outputs are the same. We want to show the inputs are the same. Since p is a positive integer, either p is even or odd. Likewise, either q is even or odd. The combination of possibilities creates 4 cases. Say p and q are both even. How can we simplify h of p equals h of q? Follow second piece. This becomes g of p over q equals g of q over 2. Since g is injective, p over 2 equals q over 2. Informally, injective is outputs equal, imply inputs are equal. Multiply both sides by 2. We get p equals q. Another possibility is p and q are both odd. Using first piece of h's rule, f of p plus 1 over 2 equals f of q plus 1 over 2. Since f is injective, the inputs to f are equal. Multiply on both sides, we get p plus 1 equals q plus 1. Subtracting on both sides, p equals q. Let's take care of p is even and q is odd. Simplifying h of p requires the second piece since p is even. The codomain of g is b, so g of p over 2 is in b. Since q is odd, simplifying h of q requires first piece, and outputs of f are always in a. Examine h of p equals h of q, assumed before breaking into cases. These in red are all equal. And clearing the red for a moment, these in red are equal to each other. And the left side of h of p equals h of q is an element of a, while the right side of h of p equals h of q is an element of b. How could these be equal? This is impossible since we were told a and b are disjoint. So we were careful and needed to discuss this case, but it turns out that this can't actually occur. There's a fourth case when p is odd and q is even. You should work out why this case is impossible too. Only 2 of the 4 cases are possible, and in those cases we showed p equals q. How would you prove 2 disjoint sets with A having 3 elements and B being countably infinite lead to the union being countably infinite? To start, since A only has 3 elements, let's call them A sub 1, A sub 2, and A sub 3. And let's clarify that A sub 1 is not equal to A sub 2, and so on. This biconditional is a useful way to say it for later in proof. Since B is countably infinite, you have the existence of a bijection. You need to define a function, let's call it h, from set of positive integers to A union B. And of course, providing the rule is the most difficult part. If the rule you define is good, then you can prove h is bijective. As a hint, think of what you want h of 1 to be. And what do you want h of 2 to be? What do you want h of 3 to be? What do you want h of 4 to be? What do you want h of 5 to be? You should at least answer up to what you want h of 4 to be, though I'd write up at least up to what up to h of 7 just to be sure. All of this scratch work of what h of 1 through h of 7 you want should be written before writing a formal rule. In the end, you want every element of A union B to be an output of H once and only once.